Welcome back to the Bugs of C++ series, the series in which we take a look at various bugs in C++ and how you can avoid them. I often say that memory is the most important thing in programming, particularly when it comes to low-level languages like C and C++. Intrinsic to memory management is lifetime. You need to be aware of the lifetime of any memory that you allocate. Now, the concept of memory might be a little bit too raw, too low level, so you can always picture this as objects. What is the lifetime of a given object that you create in C++? Fundamentally, that translates directly into memory. However, it's a bit of a higher level concept that may make more sense. This whole memory management, lifetime management situation is such a big deal that it's one of the biggest selling points of higher level languages. A language like C# or Java with a garbage collector and stronger memory management models is something called a managed language. C++ is an unmanaged language. It's up to you to manage everything. And that's a lot of power. That's a lot of power, but it's also a lot of responsibility. And very often, it's very easy to forget about this responsibility and neglect it. But what about things like smart pointers? What about all of these constructs that we can build into the language ourselves to make things happen more automatically than they otherwise would? Can't I just use them and then everything will be sweet? Well, yeah, they help, but they don't often solve the problem entirely, especially if you're not just picking the nuclear option of just do everything for me. I mean, you can write systems in C++ that make it like a managed language, and then I guess a lot of these things would go away. But the reason we're using an unmanaged language here is because we want that control and we're trying to minimize overhead. So it's a bit of a balancing act, and problems can still happen even if you do use smart pointers. And that's ultimately what we're going to be taking a look at today. What happens if we relax a little bit and we let something slip through the cracks? Let's take a look at an example. What I have over here is some code from my application architecture series. We have some really simple code here that will be called every frame inside an onUpdate function. And what it does is transition to a different layer from the current layer if a given key is pressed. Layers are a way to implement custom behavior in an application. If you're not sure what they are, check out the video I made on layers up there. The transition to function inside the base layer class allows us to transition the current layer into a new layer. Pardon IntelliSense not working as always. So in this case, it lets us, by pressing the 1 key, transition to another layer, which in this case is just a red clear color. And we can go back and forth between them. And that's also how this switch button over here via an overlay layer works as well. Software engineering can get pretty overwhelming, and usually the complexity just grows and grows. You try and keep things simple, but as time goes on, it's really hard to track everything in all of the different tools that you use and make sure that what you're doing actually aligns with everything else. Miro, the sponsor of this video, is a unified visual workspace for mapping ideas, designing systems, and collaborating in real time or asynchronously. It's a great place to model architecture, break down complex problems, plan and track work, and communicate technical decisions clearly across the whole team. With the addition of Miro AI, this potentially tedious task of translating the design and architecture in your head to an actual visual diagram that communicates that well becomes much easier. I don't know about you, but I'm not the biggest fan of making diagrams. I'd rather write some code. With Miro, I can just tell the sidekick roughly what I want, and it produces really great diagrams in seconds. Removing that friction of getting a diagram going really helps with team communication. Instead of having a meeting, for example, to discuss design, which first of all is already a bit of a challenge if you have a global team across many time zones, instead of that meeting, Miro can help me effectively communicate my ideas and design and make sure my team is on the same page. I find that I'm much more likely to do that because Miro AI lets me do this quickly without me feeling like I'm just dragging these shapes and arrows around instead of actually working. Of course, I'm still working when I'm dragging shapes around. It's obviously important to design things, but you know what I mean. For example, if I want a quick UML diagram describing the design of my C++ application architecture series, I can just type something like this, and I've already got most of the work done. You can see it's generated what I've asked, along with some placeholder example content that I can easily modify to suit my needs. From there, I can refine it again using AI, or just start doing things manually, my way. I find this really helps to unblock you from how do I start this and actually get the ball rolling, which honestly is invaluable. Miro has like 300 plus templates for you to start with, over 2,500 diagramming shapes, as well as direct integration with so many things. Jira, Trello, Miro, Microsoft Teams, and Google Meet. The list goes on. You can embed diagrams into tools like Notion and Confluence, which really helps as well. Seriously, give Miro a try today. Check out my link in the description below and play around with it on your next project. Huge thank you to Miro for sponsoring this video. Cool, so we have a way to transition from one layer to another. This app layer over here is what you see rendering the flame, and it transitions to a void layer, which is simply that red clear color that you saw. And crucially, what happens when we transition from one layer to another is we actually destroy the current layer because it's no longer alive. It doesn't need to be. We can release all the resources allocated with that layer because we don't need it anymore. We've transitioned to another layer. So over here in the destructor, we have a log message. And then every time I switched to another layer, you can see it's destroying that app layer. Then it's going to recreate it again. Then it's going to destroy it, create it, destroy it, etc. every time we transition from one layer to another. Now, immediately, what you should be thinking about is, okay, you're destroying the app layer, understandably, because you don't need it anymore. You want to release those resources and then potentially remake them in the future. But that process of destruction, you actually deleting the app layer and releasing all of those resources, where and when is that happening? Because believe it or not, something as simple as that consideration and neglecting it can lead to not only your application just flat out crashing, but even things like security vulnerabilities. So let's dive a little deeper into this transition function and see how on earth it could cause so many problems. So at the moment, you can see it calls this queue transition function. And if we take a look at this is from that layers video in my application architecture series. This is what it does. There's actually a to-do here, which I left in that series as well, that says don't do this. And this is really the topic of discussion for today's video. So what does this function do exactly? Well, it grabs a layer stack, which is a vector of unique pointers, which are all of the layers inside our application. It loops through all of them to find which layer inside the data structure is this current layer that we're calling from. Once it finds it, it replaces the current layer inside the data structure with this new layer that we would like to transition to, and then it's done its job, so it returns, breaking out of the for loop and exiting the function. Is this reasonable? I mean, I think so. If this is all of the context that you have, this is a pretty normal function. I mean, I would probably say that to an experienced C++ programmer, this would probably raise an eyebrow and be like, hang on a minute. But subjectively, I'd say it's fairly subtle. And this is also why context is so important in programming. It's also one of the most important things. Memory, lifetime, context, the list goes on. It's a lot easier to see why this is a problem when you consider the fact that this gets called from this. So we are transitioning the current layer inside the onUpdate function of the layer into another layer. Now, if we have the additional context of where this is being called from and how exactly it fits into what our application is doing this frame, then it becomes a lot clearer to see the issue. Inside our main application loop, we go through all of the layers inside the layer stack and we call this onUpdate function. Over here in app layer, one of the layers inside that layer stack, we transition to another layer, which causes us to call this code over here. We then find ourselves inside this layer stack data structure and then reassign ourselves. This is a reference over here. So we're reassigning the actual unique pointer within layer stack into this other layer that we're trying to transition to. Now, unique pointers are unique. There's one owner of a unique pointer. And in this case, it's clearly the layer stack. The layer stack is a vector of unique pointers. So this must be the only owner of each and every layer. So if we have layer at index 0, a layer at index 1, and then a layer at index 2, and then we're iterating through all of them over here, we call onUpdate on layer number 1, for example, and then within that call stack, we reassign this layer to be another different layer, and this is the owner of that layer. That layer is going to die. That layer is gone, and we're putting in another layer at index 1. What this results in is this line of code deleting the current layer while we're actually still in its call stack. So to demonstrate this a little bit more visually, if I'm in here and I press the 1 key to transition to another layer, and we have a look at the call stack, here is the main application loop inside application run. Then I go into that specific layer's onUpdate function that causes transition 2 to be called, and I'm inside the queue transition function, which deletes the current layer, but I'm still in app layer onUpdate. I'm still in this function. That just doesn't cease to exist. I'm inside this function and I've deleted this instance of app layer whose function I'm inside. So why does that even work? Because if I keep running this program, I'll get rid of my breakpoint. I can keep going between these layers with absolutely no issue. Nothing's crashing. Everything seems to be functioning as usual. Well, that is just the nature of C++. That's how it works. A function is just a function. If it's a method inside a class, it doesn't really matter. It's still a function. It's not going to suddenly explode. It's just that the actual object data has been released now. And so if we had done some additional work after this transition had taken place, this is now gone. So basically what's happened is we've deleted the current object over here. That happens inside the transition2 function. So now it's dead. It's gonna keep doing whatever we want it to do. I can print hello world over here. I'm sorry, let me do it the pro way. And if I run this, that's not going to be an issue. So there we go. I switched from this layer to this layer. You can see it destroyed app layer, but then it still printed hello world because it's gonna keep running that function. Everything's fine. What it can't do is access data that was in app layer because that has now been freed. That memory is gone. So if I had done mtime plus equals ts over here instead, you would expect that to crash. So if I transition now to something else, okay, my application hasn't crashed. Let's have a look at what's going on. So normally I'm incrementing time plus equals time step seems fine. Here it is, now time's accumulated a little bit more. That's normal. Now let's go ahead and switch out of this. That's gonna cause this delete to happen over here. And then if I come down to mtime plus equals ts, what's mtime? Oh, it's some garbage memory because it's been freed. The object has been freed. I'm still gonna actually write into that memory, but it's gone. It doesn't belong to me anymore. It's not my memory. However, I'm now going to write into memory that technically isn't mine anymore. And it's not crashing, as you can see. I'm in debug. This is a debug build and I'm not crashing. Now, of course, I can demonstrate it crashing. If we use something a little bit more complicated, a little bit more complex, like a string, let's just say mname, and I keep assigning Cherno or something over here. If I transition out of this, oh, okay, there we go. Exception thrown, can't do this, it's crashed. If we run a release build, it's not gonna crash. It's kind of dependent on exactly what you do here because it's undefined behavior. You don't really know what you're doing here. You're writing to memory that isn't yours anymore. And that's what makes this so dangerous. The fact that it's not just a crash. Crashes are easy. Crashes are great when it comes to bugs because you figure out a way to reproduce it, you figure out the underlying issue, you solve it, you then try and run it again, no crash, great, you're done. But there could be code like this sitting inside your project right now, inside whatever you work on professionally or not, that is doing this and you don't even know about it. Now, of course, you can use tools on top of C++ like address sanitizer, for example, to try and make sure that you're not doing this. However, I'm sure a lot of you haven't run tools like that, and I'm sure a lot of this does in fact slip through the cracks. So what is the solution? Well, remember when I said context is really important as well? This is specifically an issue when we transition from ourselves, right? So when we are inside the app layer on update and we run some code that indirectly sort of deletes ourselves, it's also really easy to see how exactly this is working. If I stick a breakpoint inside the app layer destructor and then I cause that to happen, then I know exactly what is destroying this object. And if I have a look at the call stack, then I can see that I'm inside app layer on update. That calls that queue transition function, which then calls the destructor. So within app layer on update, I'm calling the destructor of myself. That's what's happening here. And if I go up the call stack over here, you can see over here, this is the line of code that is causing that destructor to run. If we show the external code, we can also see how that's happening from within the unique pointer class. Now, remember when I said context is important? Context is important because this isn't always a bug. You could just shrug this off as not great design. However, it's only really a bug if we're doing it from ourselves. And obviously if we don't have any other code after this, or we do something like transition and then return, we are mitigating this bug because now this, I guess, wouldn't cause a crash as long as we don't do anything in between here that might access members and blah, blah, blah. It could just be one of those bad design things. However, if we are not transitioning this layer to another layer from within ourselves, but we're doing it externally. So if we have a look at the overlay layer, which is what has that button, that switch button, you can see that what happens when we click that switch button is we find either the void layer or the app layer externally, because we're in the overlay layer, so we're not in any of these layers, and we make it do the transitioning here. And so if we have a look at how we transition to the void layer, for example, by clicking the switch button, inside application run, we're iterating over the layer stack, yes, but the current layer is obviously not the layer that's going to get destroyed. It's the overlay layer. And so when it comes to the next layer inside the layer stack, it's going to be our new layer. So that's kind of totally fine. There's no real issue with this. It will work. And that's why the context matters. So what would be the solution to this? Well, I would queue the transition like the function name indicates. I wouldn't do it immediately. I would recognize the fact that this could in fact happen in the middle of our frame, and it probably should never happen in the middle of our frame. We should probably finish what we're trying to do and then have some kind of sync point at the end of the frame, at the beginning of the frame, doesn't really matter. Over here in application, for example, when we get to the end of our frame, everything is done. We might have some kind of post-frame event queue that goes through and actually does those layer transitions because we know we're sort of in a safe space. In more complex architectures, this can especially be important because if we have multiple threads that might be persistently running, such as like a render thread and a main thread, we'll have this section inside our frame where both threads are kind of waiting for each other. It's effectively a sync point. And that's when we can come in and do this kind of housekeeping organizational work because we know that we're not going to be in the middle of existing work taking place. I think it's fairly intuitive to realize that if you're iterating through layers inside the layer stack and you're inside the onUpdate function inside a layer, you probably shouldn't allow this very data to change. And there are clues here just by looking at this out of context as to something looking not quite right. And that is that we can see that we're dealing with unique pointers. That's what's going on over here. So presumably this is also a unique pointer and we're matching that to this. So just from the keywords, this unique pointer layer reassignment, you can kind of tell that something is not quite right because this implies that we are inside a layer, even though of course this can just be a function that's called externally. There's nothing obviously to stop this from being called internally, and that's when we wind up deleting ourselves. I hope you guys enjoyed this video. If you did, please don't forget to hit the like button. Has this ever happened to you? It's definitely happened to me before, not in this exact way, but accidentally deleting an object that you are currently inside does happen from time to time. If you guys have thoughts or ideas as to how to mitigate this and make sure that it doesn't happen, let me know in the comment section below. What other bugs have you encountered in C++? Let me know, and it might be a future episode on this series. Thank you all for watching. I'll see you next time. Goodbye.